Okay, let's go ahead and get started now with the next piece of logic here. Let's recap what we covered last time real quickly. What was last lecture all about? What do you remember from last week?
Propositional logic.
Propositions, yeah. So we were in propositional logic. We were talking about propositions. Roughly speaking, what's a proposition? Give it to me in high-level language. Huh?
Do not look at me.
Do not look at you. You got the answer. Think about it. What's a proposition? Or in other words, a statement. Statement's the word that we used last time. What was a statement? If I tell you this is a statement, what do you instantly know about it?
It's either true or false.
It's either true or false. Look at that. You came up with the answer. So a statement. A statement is a sentence that is either true or false, not both, which is essentially what we mean by proposition. So we were analyzing statements. We were analyzing things that you can either call true or false. And we introduced our 5 special symbols, these 5 operators. Can you guys sit down, okay, or should we turn off the front bank?
Can we turn off the front bank?
Yeah, if you want to grab it, it's the one to the right.
Common operators?
Yeah, so these are our common operators, our logical operators, our Boolean operators, all saying the same thing. Tell me what this symbol was. Negation or not. Perfect. So the way we're going to read that is not. And if I know alpha is true, then not alpha is false. And if I know alpha is false, then not alpha is true. So it's always given the contradiction of alpha. All right, and what was this upside down V? And. Perfect. And.
What is next?
And when is and true? When is alpha and beta true? When both are true. If one of them's false, the whole thing's false. And then what's our next one? Our B symbol? Or. And when is alpha or beta true? When at least one of them. Maybe both. So we mean it in the inclusive or sense. It includes a case where they're both true. Now our hardest one, this bad boy. What's that one? Implies. And let's just go ahead and create the truth table again for implies, because this is far and away the one that will trip you up the most, and it's the one that's the most important. It's what we use implications to encode our theorems, our proofs. It's always an implication. We go back to the Pythagorean theorem. What's a Pythagorean theorem? It's if you have a right triangle whose legs have lengths A and B and hypotenuse has length C, then A squared plus B squared equals C squared. It's an if-then statement. All theorems are. It's an implication. So let's refill out our table here. So I know alpha and beta are statements. So alpha has to be true or false. Beta has to be true or false.
Yep.
So what are all the possible combinations for these statements? What can I have here?
True,
True, true. What else?
true,
True, false. What else?
false,
False, true. And what else?
false,
Now those are all the possible combinations. If alpha and beta are 2 statements, it has to be one of those 4 things. Pick any statement that you can think of for alpha, pick any statement that you can think of for beta, it had to fall into one of these 4 cases. You had to pick
Last arrow? Like the last one?
this one?
Yeah.
That one's the equivalence, but we're still on this one.
Okay. I'm just labeling all of them.
Yep. So not and or implies equivalence. Okay. So let's fill out our truth table now for implies. True implies true is
true,
true. True implies false is false. False implies true is
true,
true, vacuously true. False implies false, though, that's
true,
still true, vacuously true. Anytime the antecedent is false, the implication is true. That one will trick you up over and over again. And then finally, logical equivalence. When did I know alpha was logically equivalent to beta? When they were both true or when they were both false. Logically equivalence just means they have the same truth value. So in this case, they're logically equivalent, and in this case, they're logically equivalent. In these 2 cases, alpha and beta are not logically equivalent. Because one's true and one's false. Not equivalent, not equivalent. Equivalent, yes. Equivalent, yes. Make sense? Another way to think about equivalence is alpha implies beta and beta implies alpha. Good? Some basic theorems that we proved last time in logic using truth tables to prove them. We showed that when you distribute a not over an and, it converts it into an or. and when you distribute a not over an or, it converts it to an and. You remember those two? So if I say, today is Monday, and I'm a billionaire, and you call me a liar, what are you saying?
Today is not Monday.
You're saying either today's not Monday, or I'm not a billionaire. One of those things have to be false. That's what it meant to call a conjunction false. Similarly, to call disjunction, when you or two statements together, to call a disjunction false, to negate it, or to call it false, what did that mean? If I said, think of something simple, you'll all be present today, or you'll all fail, and you say that's not true, what are you saying?
We all won't be present and we all
You're saying everyone's going to be present, and at least someone will pass. So when you say not a disjunction, you're saying not the alpha and not the beta. Good? And then finally, the last thing we've proved is alpha implies beta is logically equivalent to not beta implies not alpha. We are going to want to think about statements this way all the time to help us prove the statement. Sometimes it's just easier to think about this way than it is to think about this way. So let's do one this way and then state it that way. So an alpha implies beta. I say, if I'm wearing shoes, then I'm wearing socks. If I'm wearing shoes, then I'm wearing socks. Says the exact same thing as, if I'm not wearing socks, then I'm for sure not wearing shoes. This says, if I'm wearing shoes, then I'm wearing socks. This says, if I'm not wearing socks, I'm for sure not wearing shoes. See, intuitively how they encode the same thing? Okay, now remember, we came across our first predicate last time was this, x plus 2 equals 5. This is not a statement, this is a predicate. So it's not a proposition, it's not a statement, it's a predicate, something new now. Now what's the difference between this and the statements we've been looking at? It has a variable, it has this x. You need to plug in a term in order to determine whether or not this is true or false. You can't call it true or false on its own. So that's what a predicate is. It's just something that needs a term to decide whether or not it's true or false. So, shifting now into predicate logic. I'm going to say the exact same thing in slightly more precise language. A predicate is a proposition valued function. What does that mean that it's proposition valued? It means it spits out a proposition. You give it a term, and it spits out true or false. So it's something that needs a term in order to decide whether or not it's true or false. Takes in a term, spits out true or false. That's a predicate. And it can be in terms of some number of variables. Maybe one, maybe multiple. In other words, if you give a predicate its terms, then the result is a statement. The result is a proposition. The result is something that is either true or false. We have a special word for predicates that take exactly two terms, and we call them relations. A relation, just a special type of predicate. All right, so let's do some examples. Let's look at the is Brown predicate. Question, is Brown? True or false? Is Brown? Bad question. It's not a proposition, it's a predicate. On the other hand, I say, this desk. I plug this desk in for X now. I say, this desk is brown. Now you can call it true or false. We'll say true, a light brown. So you pass the desk into it, the result is true. You pass me into it, the result is false. So is brown is a predicate. You can also call it X is brown. The X there is just a placeholder specifying where the term goes. So here's the is brown predicate. Takes one term and spits out true or false, depending on what you give it. Let's look at a two-term predicate. The X likes Y predicate. This one is now also a relation because it takes two terms. If you give me the two terms, I can tell you if it's true or false. If I plug in Jack and Jill, it returns true. If I plug in Jack and Samantha, it returns false. Make sense? But by itself, it doesn't make sense. Likes, true or false? Doesn't make sense. You need to give me the terms. So that is a two-term predicate. A predicate that needs two terms to call it true or false. Or in other words, a relation. Here's is greater than 2 predicate. I plug in 5, it returns true. I plug in 1, it returns false. X is greater than 2 by itself, doesn't make sense. Or this is Bob's best friend predicate. Again, plug in Bill, it returns true. Plug in George, it returns false. Good? Some examples of predicates. So now let me read the definition one more time, and hopefully it completely sinks in. What is a predicate? A predicate is a proposition-valued function. It returns a proposition valued function of some variables, potentially more than one. In other words, if you give a predicate its terms, then the result is a statement. The result is something you can call true or false. That's a predicate. Good? Okay. Now, just notation. For a single variable predicate, we typically write some capital letter, and then what we're going to use is our variable. So this might be the is pink predicate. There's how we might symbolize it on a piece of paper. And then for a two-term predicate, you might see it like this. So here's how we might symbolize some relationship. This might be the is quicker than relationship, and you plug in x and y. It returns true if x is quicker than y, returns false if x is not quicker than y. Specifically, in the case where we have a two-term predicate, which is also called a relation, in the special case where we have a two-term predicate or a relation, it is often the case that rather than writing the relation this way, we put the name of the relationship in between the two symbols. Going back to basic algebra, here is a relation that you've used 1,000 times, the less than relation. This is perfectly valid notation. Less than applies to 1 and 2, or in other words, 1 is less than 2. We always write that relation this way. 1 is less than 2. So in the special case, so here is one of our relations, the less than symbol. That symbolizes a relation, two-term predicate. In the special case where it's a relation, it's very common that we write the name of the relation in between the two variables, as opposed to writing it this way. This notation's fine, but nobody uses it. Make sense?
Yeah.
So there's some examples of predicates. Proposition, something that's true or false. Predicate, something that returns true or false when you give it its terms. Okay, any questions so far? Nothing? Okay. So for each of the following, you're going to tell me whether or not, you're going to tell me if it's a statement or a predicate. With me? Statement or predicate? X is blue. Predicate. Jack is taller than Jill. Statement. Right? This is something you could call true or false. Y is greater than 2. Predicate. 2 plus 2 equals 4. Statement. X loves Y. Relation. Predicate. Two-term predicate, relation. So predicate is a correct answer. This is a predicate. It just happens to be a two-term predicate, which we can also call a relation. Good. Go home. Neither. You can't call it true or false. It's not a predicate. It's not a relation. So it's not like everything falls into either the predicate or the relation. Sorry. It's not a proposition, and it's not a predicate. I don't know what I was saying before. Not everything falls into a predicate or preposition category. It could just be something else altogether. So go home. It's just words. It's not a statement. It's not a predicate. X is greater than or equal to 2. Predicate. Single term predicate. X, Y, and Z are triplets. Predicate. If you plug in X, Y, and Z, I can now tell you if it's true or if it's false. Good? Jack is taller than X. Predicate. X is blue and Y is greater than 2. Predicate. And it's a relation. It's a pretty useless relation. Well, I don't know when we'd ever use the first thing is blue and the second thing is greater than 2 relation, but it's a perfectly valid relation. It's just not one we're going to be particularly interested in. So not all of them are necessarily useful. We can come up with way more unuseful ones than useful ones. But still, a perfectly valid relation. The first thing is blue and the second thing is greater than 2 relation. That's a fine relation. Okay, so there's some examples of predicates. Now, since predicates are proposition valued, we can use logical operators to combine predicates together. So I can let P be the predicate, X is greater than 2. So this is greater than 2 predicate. That's what P of X stands for. So if I plug in 1 here, then P of 1 is false, because 1 is not greater than 2. P of 5 is true. So when I plug something in, this thing is going to be true or false. Similarly, Q could be the predicate Y loves Z. It's the loves predicate. Plug in Jack and Jill, it returns. Plug in Jack and Samantha, it returns
False.
for Samantha. Okay. So since these things return true or false, you can use predicates to define new predicates with our logical operators. So I can define a new predicate R now, which takes three things, and I can define R to be, probably the first time we're seeing this notation. That colon there means I'm about to define a new symbol on the left-hand side, and I'm going to define it in terms of symbols on the right-hand side, which should have already been previously defined. So we already know what the P is here, we already know what the Q is here. I'm going to define now a new term, a new predicate R. R takes three terms, x, y, z, and I'm defining it to be logically equivalent to x is greater than 2 and y loves z. Defining a new predicate in terms of existing predicates. So now R is a x is greater than 2 and y loves z predicate. It's a useless predicate, but this way of defining it makes perfect sense. So I can take predicates and I can AND them together. Because ultimately, this just returns true or false. Ultimately, this just returns true or false. And you know how to AND two things together that are true or false. Same thing if I replace that with an or an implies, or I could have used a not somehow. And so we can apply logical operators to both propositions / statements, and we can also apply those logical operators to predicates, and it still makes sense. Because even though you can't call a predicate true or false, what it returns is ultimately going to be true or false. So I can still AND two predicates together, or two predicates together, just like I could a proposition. That's what I'm trying to stress here. Does that all make sense? So it's perfectly valid to use those symbols when defining some predicate. Okay. So I'll give you an example. Let's assume that we've already defined the less than predicate. And it returns true when x is less than y. And we define this equals predicate, which returns true when x is equal to y. Then we can define some new predicate. We're going to call it the less than or equal to. And what do we define it to be? We define it to be either less than applies to x and y, or equals applies to x and y. So you can define less than or equal in terms of less than and equal. Defining a new symbol using existing symbols, which is already how you think about x is less than or equal to y. So there's a way we could define it on paper, assuming we already knew had the less than and equals defined. Does that all make sense? And then again, with relations, we can write the name of the relation in the middle. What's a relation? Two-term predicate. So when it's a relation, when it only has two terms, we can write the name of the relation in between our two variables. So rather than writing it this way, which is probably harder for you to consume, you can write it this way. What does it mean for x to be less than or equal to y? Well, that's logically equivalent to x is less than y, or x equals y. And that's what it means for x to be less than or equal to y. Make sense? So examples of using predicates and applying logical operators to predicates. Okay, now our quantifiers. Very scary symbols. So far, the scary symbols that you had to get used to were not, and, or, implies, equivalence. Going to give you two new scary symbols today that you got to get used to. Fortunately, there's only two new scary symbols today. The new scary symbols are the for all symbol, kind of like an upside down A, and then our last one is going to be the existential quantifier, which is just a backwards capital E.
Would this be added into the common operators?
These will not be operators. These are going to be what we call quantifiers. So they're different. I'm just showing you all the scary symbols I'm going to use.
How do you
So,
spell quantifiers?
Quantifiers. So those are the only two new scary symbols you're going to see today. I'm going to use them all the time, so you just got to get used to them. Okay, so our scary symbols. First we have our universal quantifier, this upside down A. We typically read it as for all, for each, or for every. That's how you read it. It's called our universal quantifier. And then we have our existential quantifier, this backwards E. We typically read it as some or there exists. I'll typically read it as there exists. Now I'm just going to read some statements now with these quantifiers. What does this say here? Scary notation. This says for all x, x is greater than 2. That's just reading it right outright. This one says there exists an x, x is greater than 2. That sounds weird. In English, anytime after we read an existential quantifier, we always say when we get to the parentheses, such that. And it just reads better in English. So we read this as there exists x, such that x is greater than 2. And that's how I will always read those. For all x, x is greater than 2. There exists an x, such that x is greater than 2. Now notice something amazing. X is greater than 2. True or false? Bad question. It's a predicate. For all x, x is greater than 2.
False.
False. Are all numbers greater than 2? No. So you were able to call this false. Notice something crazy happened. You had a predicate, and you added a quantifier on it, and that suddenly turned it into a statement or a proposition. So there's two ways we can convert a predicate to a proposition. One way is we can plug in the term. I can replace the x with like 5, and now it's either true or false. The other way I can do it is I can add on this quantifier, and that will make it something that's either true or false. Make sense? Okay, and check this one out. There exists an x such that x is greater than 2. It's true. Does there exist something greater than 2?
Yeah.
Yeah, we call it 7. It's the only one. There's infinitely many things greater than 2. But notice, once again, adding this quantifier or this quantifier took our predicate and converted it into a proposition, into a statement, into something that's true or false. Typically, we write the quantifier in parentheses followed by the predicate, where the quantifier uses the same variable that you chose in your predicate. The choice of variable is completely irrelevant. If I instead said for all y, y is greater than 2, it says the exact same thing. There's nothing special about x's and y's. You can plug in any variable you want. You can use any symbol you want. Okay. We can also chain quantifiers together. So I'm going to, let's see. So I'm going to do for all x, for all y, x plus y equals, what was I doing, zeros? Yeah. Next we're going to look at for all x, there exists a y, such that x plus y equals 0. Next we're going to do, there exists an x, such that for all y, x plus y is equal to 0. And then finally we're going to do, there exists an x, and there exists a y, such that x plus y is equal to 0. Just trying to get you used to these quantifiers and applying them to statements. So lots of scary symbols. Let's read out what this says. In each case, you're going to call it true or false. So what does this one say? This says for all x and for all y, x plus y equals 0.
False.
False? For all x and for all y, x plus y equals 0. Yeah, this says pick any two numbers, their sum is 0. That's obviously false. Let x be 1, y be 7. 1 plus 7 is not 0. Okay, what does this one say? This one says for all x, there exists a y, such that, remember, after the existential quantifier, say such that for all x, there exists a y, such that x plus y equals 0. Is that one true?
Yes.
This says for any x, there exists a y such that x plus y equals 0. So then for any x I choose, you should always be able to find the y such that their sum is 0. So if I pick 10 for x, then you say
Negative 10.
-10. If I pick pi, you choose
Negative 5.
-pi. If I choose negative pi, you choose
Negative pi.
or pi. Good. So yes, in that case it's true. All right, let's read this one. There exists an x such that for all y, x plus y equals 0. True. There exists an x such that for all y, x plus y equals 0. There exists some magic x out there such that for any y you choose, their sum is always 0. What is that magic x?
Negative 1.
-1? -1 plus anything is 0?
Negative y.
Negative y? but you don't have a y yet. This says there exists some number, such that no matter what number I choose, their sum is always 0. This is false. There is no magic number in existence, such that for any y, their sum is 0. For any y, for any x, I can then go find a number, such that their sum is 0, but there does not exist some magic number in existence, such that for any y, their sum is 0. Order matters, and it matters a lot. Try and say it without the y's and the x's. For any number, there exists some other number that makes their sum 0. True. This one says, there exists some number, such that for any other number, their sum is 0. False. Those are two very different things. And finally, our last one. There exists an x, and there exists a y, such that x plus y equals 0. Does there exist an x and a y in existence such that x plus y equals 0? Can you find two numbers that add up to 0? Yes. So this one is true. Okay, we're going to play the game again. This time we're going to replace all the pluses with times. And think through them one more time. Try and get used to this language. So what does this say? This says for all x and for all y, x times y equals 0. Is that true? No, it's false. Perfect. Let's try the next one. For all x, there exists a y such that x times y equals 0. Is it true that for any x I choose, you can find a y such that the product comes out to 0?
Yes. Wait. Yes.
I choose 17.
I choose 0.
You choose 0. I choose 197.
I choose 0.
You choose 0. Okay, so it is true that for any x I choose, you can always find a y such that the product comes out 0. True.
You're kidding me. You don't have to write it out?
Don't have to write it out.
That is so cool.
For the first couple lectures.
Oh, okay. I'm taking roll.
We are missing Caleb Dockstader.
And that's it?
And that is it.
Okay. Okay, thank you
Thank you.
very much.
Alright, so we just did this one. For all x, there exists a y such that x times y equals 0. That one's true. Let's try this one. Does there exist some magic x out there such that for all y, x times y equals 0?
Yes.
In this case, it's true. And that magic x is 0. There exists an x, namely 0, such that for all y, x times y equals 0. And then finally, do there exist an x and y such that x times y equals 0?
Yes.
Yeah. What could our x be?
0.
0. And what could our y be?
Negative.
9. 0 times 9 equals 0. Just have to find one example. Then there must exist an x and exist a y such that x times y equals 0. Okay, so the point of that exercise was getting you comfortable with these quantifiers, stringing quantifiers together, and notice how the order on the quantifiers matters. The for all followed by a there exists is very different from a there exists followed by an all for all. Okay, so getting used to some of this notation. We won't get into okay, we can do this. This is a bit much for your first time in logic, but for you guys who have been through it a couple more times, you'll like this more. So now we're going to define the for all x, there's a p of x. So here's its definition. Let a p of x be a predicate, then for all x, p of x is a proposition. That is true if and only if p of x, the predicate, is true independent of our choice of x. Otherwise it's false. There's its precise definition. Those of you, this is your first time through it, you don't need to worry about that. Give you an example. For all x, x is greater than x, we call that true because this is true independent of our choice of x. It is always the case that x is greater than or equal to x. Otherwise, for all x, x greater than or equal to 2, there's an example where it's false because this isn't true independent of our choice of x. Now, how do we define the existential quantifier? We define it in terms of the for all quantifier. By definition, there exists an x such that p of x. We define that to mean that it is not the case that for all x, not p of x. So for those of you who have been through logic again, Those are exactly how we construct those definitions. And so everything's well defined in our system. Now, for those of you who haven't been through logic before, and this is your first time, the only thing I want you to pay close attention to is this equivalence. So pretend that this isn't a definition and it's just an equivalence. This is how everyone thinks about negating. Is they think about it in terms of when we distribute a not. Notice if we start with this. So for all x not p of x. If I want to negate that, then that gives me this same thing. And so it switches when I negate a for all x not p of x. It switches up for all into a there exists. And it negates whatever the predicate was. In other words, when I do something like not, well, let's start with this. Imagine I was looking at some predicate like this. For all x p of x, and I want to negate that. So imagine I want to negate this. You did this over and over again. Let's think of a p here. P could be plays golf. So this would be for all x, x plays golf. Or another way that we say this is all men play golf. And let's imagine that we want to now negate this. We want to come up with the negation of this statement. So what does it mean to say not all men play golf? The way that we do that is when you distribute a not over a quantifier, it switches a quantifier into its opposite. So for all's going to there exists, and there exists going to for all's. And then you put the not on the inside. So the negation of all men play golf is there exists someone that does not play golf. So not all men play golf is the exact same thing as there exists someone who does not play golf. And you did this exercise over and over again. So give you intuition, and that's just applying your logical operators to these two things here. So this is telling you how you distribute a not over a for all, or for all, a not over there exists. If these two things are logically equivalent, let's negate both sides. What does it mean to say that it is not the case that there exists someone that plays golf? If I negate this side, I've got to negate this side, and it just gets rid of that quantifier right there. To say it is not the case that there exists someone who plays golf means that for all x, they do not play golf. Make sense? So this is the way that we think about these quantifiers in our head. Once you get comfortable with logic, you don't have to carefully think it through every single time. What does it mean to say the negation of all men in Georgia are less than 6 feet tall? Nobody is going through the pains of actually trying to carefully think it through in their head and make sure it appeals to their intuition. They're just performing this calculation. How do I negate a for all? I convert it to a there exists and distribute the negation inside my predicate. And that's the way we do it. Let me try, let's see, what would have one of your homework problems have been? It would have been something like for all x, we'll distribute it to 2. How would we do something like all men play golf, and what's something else men all do? Watch football? So here is something like all men play golf and watch football. P of x is a plays golf predicate. F of x is a watches football predicate. With me? So this says for all x, x plays golf is true and watches football is true. Now imagine our job was to negate this thing. So how now would I negate something like this? Just going through the algebra without even thinking about it. When I negate this, I switch my for all to a there exists, and I distribute the negation to the inside. So now I'm going to do not p of x and f of x. How do I distribute a not across an and?
Change it to an or.
Change it to an or. So this turns into there exists, such that we have not p of x or not f of x. And that's just calculating it through. So what does it mean to say that it is not the case that all men play golf and watch football? It means to say that there exists some man, there exists at least one person, or you can also say some men. Some men do not play golf or do not watch football. That's what it means to say not all men do it. It means to say some don't do the first or don't do the second. And that's just carrying through the algebra, using this equivalence and using the theorem that we had from predicate logic or from proposition logic before on how we distribute nots. So that's how you negate it. So when you apply a negate here, you convert the there exists into a for all, and then you negate the inside. So going from right to left is distributing that negation. Pull the negation on the inside, and you convert the there exists into a for all. Because not is the same thing as just a statement. Not alpha is just... What is not alpha?
Alpha.
It's just alpha. So if I distribute that to the inside, let's rewrite that. We switch the quantifier to a for all x, and then we have a not p of x. What is not p of x? Just p of x, which is exactly what we have over here. So that's how you distribute quantifiers, or distribute negations over quantifiers. Let's do another one. Here we have a not for all x p of x. Let's distribute the not. If I'm going to distribute the not, I'm going to bring it to the inside, and I convert the for all into a there exists. So we convert the for all into a there exists, and we move the not to the inside. Last one. If I want to distribute this not over there exists in x such that p of x, I switch the there exists into a for all, and I put the not on the inside. Let's apply words to each of these just to help. We'll pretend that we're talking about swans, and we'll do the p is white predicate. So this says, for all swans, a swan is white. Or in other words, this says all swans are white. That's going to be the interpretation I'm applying. With me so far?
Yeah.
So saying, for all x is white, or for all swans, that swan is white, or all swans are white, is logically equivalent to saying, it is not the case that there exists a non-white swan. All swans are white. It is not the case that there exists a non-white swan. If there does not exist a swan that's not white, then all swans must be
White.
white. If there isn't one in existence that's not white, then they must all be white. It is not the case that there exists a non-white swan. It says the same thing as for all swans, they're white. With me? Let's try this one. Not all swans are white. It's not the case that for all swans, they're white. Not all swans are white. What does that mean? That means that there exists a swan that's not white. If not all swans are white, then there exists a non-white swan. Try to make this one appeal to our intuition. If it is not the case that there exists a white swan, it is not the case that there exists a white swan, it is the same thing as for all swans, they're not white. If there does not exist a white swan, then all swans must not be white. Good? Trying to apply intuition to it? So you are already going through the logic in your homework problems of this type of thinking. Now here's the algebra for how you would do that. Just expressing it in symbols and without even having to think about it, just carrying it out. Make sense?
Yeah.
Okay. Those were examples from your homework. We won't go over those again. We'll go over your homework at the end of class. Okay. Now I told you that every field of mathematics is simply determining the logical implication of some given field axioms. Remember, every field of math has four components. You have the axioms, the undefined terms, the definitions, and the theorems. Right? Now, why do we have to have undefined terms? Because you can't define everything. Otherwise, it would ultimately be circular. It's the same reason you can't learn French from a French dictionary if you don't already know any French words. You're going to look up a French word and you're going to see a bunch of other French words. Eventually, we have to start with some words that aren't defined. So in every field, we're going to have our axioms, our undefined terms, our definitions, and then our theorems. So you have to have undefined terms so that you can start defining things. The only way I can define a new word is if I start with words that aren't defined, and then use those to define a new word. Otherwise, I can never define a new word. Because I'd have to give you words that were defined somewhere else, and then it'd be an infinite regression, or it'd ultimately be circular. Our axioms are what give our undefined terms meaning. Going back to geometry, one of the simple ones you were given is, one of the axioms is every line has at least 2 points. Point is not defined and line is not defined. There is no definition of point, there is no definition of line. But whatever those objects are, every line has at least 2 points, whatever that means. So the axioms were what gave those terms, point, line, and plane in geometry, your axioms are what gave it meaning. And then you came up with a definition for something like a line segment. What is a line segment AB? It was all the points. It was the points AB. Oh, sorry. This is using the word between. I don't know if you remember that far back to your geometry. You remember between? So between was also one of your undefined terms, what it means for a point to be between. But when you defined it a line segment A and B, you said it's a point A. Wait, what's the definition of point? Bad question. The point B, what's the definition of B? Or point B? Bad question. And all the points between them. So we didn't know what point was and we didn't know what between was, but we just defined now line segment. So a line segment was a defined term in your geometry, and we used point lines, or sorry, we used point and betweenness to define it, undefined terms. So you have to start out with some undefined terms and use those to construct your definitions. So every systematic, or every axiomatic system, every system of mathematics is an axiomatic system, and it has these 4 things. It has its axioms, its undefined terms, its definitions, and its theorems. 99% of mathematics is just focused on theorems, proving theorems, and creating definitions as we go. So the heart of mathematics, I guess you could say, is these 2. Hardly have to spend any time on these. Once you introduce those, you're done. And now it's just about creating definitions and theorems. Okay? Now, how do we actually construct a proof? How do we prove some theorem? So remember, a theorem is a statement that is going to be a logical implication of your axiom. So I've got a bunch of axioms which are statements. Call this statement alpha. All right, and I want to know, so this statement in particular is alpha. And I want to know, is this other statement beta true, which we would call a theorem of the system. How would we prove that? We need to show alpha implies beta. I need to show alpha implies beta is true. Because if I know that alpha is true, and I know alpha implies beta is true, then what must I know about beta?
It's true.
It's true. So all the math, we're always proving the alpha implies beta part. If I know alpha, and I know alpha implies beta, then I know for sure beta. If you know the implication, if I'm wearing shoes, then I'm wearing socks, and you know I'm wearing shoes, what do you instantly know? I must be wearing socks. That would be the beta in our circumstance. So if you know alpha, and you know alpha implies beta, you instantly know beta, your theorem. So when we prove a theorem, it's always about showing alpha implies beta. We show if the antecedent is true, or if our axioms are true, then the beta must also be true. That's what you might say an implication says. What does it mean to say alpha implies beta? It means if alpha is true, then beta is true. That's what it means to say alpha implies beta. Might be worth it writing out the truth table for this. So I'm going to write out the truth table for this right here. If you know alpha, and you know alpha implies beta, those things together imply beta must also be true. In other words, this whole thing right here is going to be what we call a tautology. It's something that's always true. So this one, we'll write it out, and then I won't bother with the other ones. So we have alpha, beta, alpha implies beta, and then finally we need to do alpha and alpha implies beta. And then we need to do, I may have marked this whole statement just as S, so I don't have to rewrite the whole thing up here. S. With me? So let's write this out. I have how many statements how many component statements do I have? Just alpha and beta. What are all our possible combinations for alpha and beta?
True, 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 false.
True, 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 false, false, true, false, false. Okay. So it always has to be one of those four scenarios. All right, let's see. True implies true is?
True.
True. True implies false is?
False.
False. False implies true?
True.
Vacuously true. False implies false, so
True.
still true. Vacuously true. Okay. Now we're going to AND together alpha and alpha implies beta. Here's alpha, Here's alpha implies beta. We're going to AND these two together. True and true is? True. True and false is? False. False and true is? False and true is? False. Okay, now what was our S here? Let's read our S one more time. Our S says, if you know alpha, and you know alpha implies beta, maybe you should have put square brackets right there to really clarify how the implication goes. If you know alpha, and you know alpha implies beta, then you know beta. We're saying that statement is always true. It is always and forever the case that if you know alpha, and you know alpha implies beta, then you must know beta. That's what the statement S says, okay? So that's statement S. We're going to now write it right here. What is the statement S saying? It's saying all this, is saying this column implies beta. So we're doing this column implies beta. This implies this, is what we're going to write in this column. You with me?
Cool, yeah.
So true implies true is?
True.
False implies false is?
True.
False implies true is? False implies anything is true, so vacuously true. And then finally false implies false is? True. And notice that this statement, S, is always true. No matter what values of alpha and beta you plug in. Pick any statements, alpha and beta, you want. One of them had to be true, one of them had, or alpha had to be true or false, beta had to be true or false. If you happen to pick true statements for alpha and beta, then S, this whole statement here, comes out true. If you happen to pick a true statement for alpha and a false statement for beta, this whole statement still comes out true. No matter what two statements on planet Earth you choose for alpha and beta, plug it in and evaluate it. It will always and forever come out true. That's what we call tautology, always true. This is what we're doing in a proof. We are demonstrating that if you know alpha and you know alpha implies beta, then you must know beta. That's the heart of proof right there. Now I can reconstruct the same thing with this statement. Here's another way that we do it. If you know not beta, and you know alpha implies beta, then you know not alpha. Now that one seems weird at first, but let's write the contrapositive of alpha implies beta. What's the contrapositive of alpha implies beta? What's the contrapositive?
Not beta.
It's not the conclusion implies not the antecedent. Alpha implies beta is the same thing as not beta implies not alpha. Going all the way back to the very first thing we talked about when we did our review. This right here. Alpha implies beta is the same thing as not beta implies not alpha. Let's put it in words. If I'm wearing shoes, then I'm wearing socks, says the exact same thing as if I'm not wearing socks, then I'm not wearing shoes. They'll say the same thing. Okay. Find the slide we were on. This one. So alpha implies beta is the same thing as not beta implies not alpha. Okay, so if I know that not beta is true, and I know not beta implies not alpha, what do I instantly know? I know not beta, and I know not beta implies not alpha. What do I know? If I know that not wearing shoes implies not wearing socks, and I know that I'm not wearing shoes, I said that backwards, didn't I? If I know not wearing socks implies not wearing shoes, and you know that I'm not wearing socks, then you know I'm not wearing shoes. That's what you can conclude. So this says the same thing as that, and you see how this has the exact same form as this. Just replace your alpha with not beta, and your beta with not alpha. So it says the exact same thing. So if we were to write out the truth table for this or for this, it would also always be true. So that's the logic at the heart of our theorems. Okay, and then finally, what we call a proof by contradiction, the logic of that. If I know alpha implies something impossible, if alpha being true implies something that is for sure false, f there is not a variable now, f is false, something that's for sure false. If alpha implies something that is for sure false, then alpha must be false. It can't be true. You with me? I'll give you an example. I tell you, I was in Salt Lake City 10 seconds ago. Me being in Salt Lake City 10 seconds ago implies I traveled stupid fast, which is impossible. Therefore, I lied to you. I was not in Salt Lake City 10 seconds ago. You use this type of thinking all the time. You're not sure if something's true. If it were true, that would imply something impossible. Therefore, it can't be true. So it must be false. So if you know alpha implies false, then alpha must itself be false. Or in other words, not alpha is true. Same thing. Good?
Yeah.
I know that's a lot to swallow with all these ways of doing proof. But cover it once formally, and then you'll just get used to it as we construct these proofs. When we get to actually proving things, it's going to feel a lot simpler than all the overhead for getting there. Okay, so that's it for predicate logic. Now, last thing we need to touch on is logic now with identity. Remember, there's three pieces to logic. There's propositional logic, predicate logic, logic with identity. So I'm actually going to give you one more scary symbol now, but it's one you know them of. It's the equal sign. That's what we mean by identity equals. That's it. Now there's two rules of logic governing the way equals works. We call the first one the law of identity. We call the second one the principle of extensionality. What does the law of identity say? It says everything is identical with itself. It's often stated as A is A, or the way that we'll write it for our purposes is for all x, x equals x. That's always the case. For any x, x is equal to itself. You always know everything is identical to itself. That's the law of identity. Good? Second piece of that is called the principle of extensionality. What this means is that equals may be substituted for equals. So we're now going to do some proofs using just these two laws. So here's the first thing we're going to prove. We're going to prove that if A equals B, then A plus C equals B plus C. Now this has nothing to do with arithmetic. We did not get to arithmetic yet. We're still just in logic. This is going to be a consequence of logic, that A plus C equals B plus C, not a consequence of arithmetic. This has nothing to do with arithmetic yet. It was shocking to me how long it took me to make this discovery. Because I wondered how on earth, as I was going through my education, do we know that A plus C is equal to B plus C? Where do we get that? When I would look at the axioms of arithmetic, nothing gave us that. How are people magically doing this operation? It's because it's more foundational than arithmetic. It's logic. It's a consequence of just these laws. We haven't said anything about arithmetic yet. So regardless of what A and B mean here, and what that plus symbol means, this is still true. As long as these symbols are all defined. So now with just logic, forget that you know anything about arithmetic, I'm still going to prove that this is true. So one, construct, so we're going to do a proof now. I'm going to prove if A equals B, then A plus C equals B plus C. Writing out our first proof of the class. You with me? Now, what we're trying to prove in a proof is that alpha implies beta. I'm trying to show alpha implies beta. I'm trying to show if this is true, then this is true. That's how I prove something. So the way that we prove alpha implies beta is we assume the antecedent and show that implies the conclusion. Let me draw just a little truth table here. It never hurts to overstress it. Alpha implies beta. So I've got some statement up here. I need to show alpha implies beta is true. So true, 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 false, false, true, false, false. There's all the possible combinations, right? And we know that this comes out to true, false, true, true. We've already done this a few times today, right? If I want to show alpha implies beta is true, I need to show it is not this case. I need to show that we do not have this case. If we do not have this case, then alpha implies beta is for sure true. Okay? Now, if alpha is false, alpha implies beta is automatically true, vacuously true. So I don't care about the case where alpha is false. If alpha is false, beta is then our implication for sure works. If alpha is false, alpha implies beta, we're good. Don't need to think about it anymore. If alpha is true, beta better be true. So I'm going to prove if alpha, then beta. That's what I'm proving right here. I need to show that it's one of these three cases. Right? or show that it's not this case. In other words, I need to show it's not this case. I need to show it's not false. I need to prove it's true. So if alpha is false, if alpha does not equal b, then we're in one of these two cases. Or sorry, if a does not equal b, then we're in one of these two cases. If alpha is false, my whole implication is true. I don't need to worry about that case. All I need to worry about now is if alpha is true, then beta is also true. And if I can show that, then I've proven the implication is true. That make sense? So, I'm going to say let A equal B. Or in other words, let alpha is essentially why I said that. Assume your antecedent is usually what the first line of your proof is going to be. It's going to be let whatever alpha says. Let A equal B. Sorry, that's a B, not a beta. Don't let me confuse myself. Let A equal B. So we are assuming alpha is true. We are assuming our antecedent. What if alpha is false? We don't care about that case because the implication is obviously true. All we care about is when alpha is true. So assume our antecedent, or let alpha be true. Now I need to show beta is also true. Otherwise, our implication doesn't work. If alpha is true and beta is false, then our implication is false. So I need to show if alpha is true, then beta is also true. So let alpha. Now, I know the last line of my proof is going to be beta. So down here, last line, however many lines it's going to take me, I don't know yet. But the last line of my proof is just going to be, therefore, beta, whatever our beta is. I need to connect the alpha to the beta. If I can show the alpha being true, dot, 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 leads to our beta being true, then alpha implies beta, and we're done with our proof. That's what it means to prove something. You with me? So I know the first line of my proof is always and forever let alpha. I know the last line of my proof is always and forever, therefore, beta. Now I need to find a way to connect these two things together. So let A equal B, or let alpha. Now I'm going to have to use my rules of logic to somehow show that that leads to beta. Okay, so then, second step here, I'm going to say A plus C equals A plus C. How on earth do I know A plus C equals A plus C? Everything is identical to itself. I can always and forever write some symbols is equal to those exact same symbols. So whatever A plus C is, doesn't matter. I always and forever know A plus C is equal to A plus C, whatever that is. Because everything is identical with itself. So I just barely used here to justify this line, the law of identity. Those of you who have done two-column proofs, over here in your second column, you would have written law of identity there. All right, so 3. I know A plus C equals A plus C. Then I know A plus C is equal to B plus C. How on earth did I get from here to here? I replaced that A with a B. How do I know I can replace an A with a B? Using the principle of extensionality, I know equals maybe substitute for equals. Since A is equal to B, then I can at any point substitute an A for a B, and my statement is still true. So getting from here to here, justifying this line, that was using the law of identity, everything's identical with itself. Getting from here, this line to this line, I use the principle of extensionality, which says equals maybe substitute for equals. And then so here we have line 4. Therefore, A plus C equals B plus C. And there we did it. We constructed our first proof. Our antecedent, our conclusion, and we justified every step in between. With me? Now I guess one more special symbol. It's going to be your favorite symbol every time you can write it. Square box. What does square box mean? It means, and thus it is demonstrated. We used to write QED, which was some Latin phrase for and thus it is demonstrated. Now we do a square box. Because who wants to keep track of the Latin phrase? Dead language. Okay, so there we go. We just did our first proof. Now, we're going to prove, not only is it the case that if A is equal to B, A plus C equals B plus C, it's also the case that if A equals B, A times C equals B times C. You ready? How do I prove that if A equals B, then A times C equals B times C? Step 1, assume the antecedent. Let alpha. Step 2, write your conclusion as your last statement. Therefore, A times C is equal to B times C. Now I got to justify all my steps in between. How do I justify this step? Then A times C equals B times C. Or A times C equals A times C. How do I know A times C equals A times C? Law of identity. Everything's identical to itself. And then replace the times here, or the plus with times here. Therefore, A times C equals B times C. How do I know I can replace that A with a B? Principle of extensionality. Equals maybe substitute for equals. And so there we go. We just really proved that if A equals to B, then A times C equals B times C. Right? And again, notice how we do not care what on earth the operation was here. And so now, this is true for any operation you can plug in here. Notice that we had nothing to do with arithmetic yet. We didn't care what plus was. We didn't care what times was. So for any operation, call it circle. If I know A is equal to B, then A circle C is definitely equal to A circle C. Whatever circle means, that's true because of the law of identity. Then A circle C is equal to B circle C. That's true because of the principle of extensionality. And therefore, A circle C equals B circle C. So if I know A equals B, and circle is any well-defined operation, A circle C is equal to B circle C. And you can always do that no matter what field of math you're in, what the operation is. The A's, B's, and C's here don't have to be numbers. They could have been functions, and this could have been function composition, for those of you who know what that is. You've done function composition before? This proves that if A and B are equal functions, then A compose C is equal to B compose C, whatever those functions are. Doesn't matter what the A's, B's, and C's here are. Doesn't matter what operation that circle represents. It proves it for all of them, as long as it's defined. Make sense? So there we go, using some logic. Now we're going to be doing a lot with, we'll skip set theory. We'll eventually get to set theory in this course, so I'm going to skip that for now. And so now, in this class, over and over again, we're going to be working with fields. We're going to be working with, fields of mathematics, where we're using the real numbers. So I'm giving you more foundations than what you're going to need for your book and for your homework. This is just to be completely explicit. These are all the unstated things. These are the axioms on the real numbers, the field axioms. Those of you who know a little bit more, we're skipping the completeness axiom. Those of you who don't know what we're saying, good. Here are the axioms on the real numbers. These are the only 10 things we assume for all the algebra you do in all your algebra courses. It's just these 10 statements. These are 10 axioms. And these are undefined terms that show up in the axioms. So for each pair of numbers, x and y, there exists a number called their sum, denoted x plus y, and a number called their product, denoted x times y, satisfying these operations. Here's the things you can assume here's all the things you assume you can do with numbers. You assume for all x and y, x plus y is equal to y plus x. You assume it doesn't matter what order you add in. 1 plus 2 is the same thing as 2 plus 1. You can't prove that. That's an assumption. You have to use that assumption to prove later things in algebra. This one says for all x, y, and z, if you add the x and y together first, and then add the z, that's the same thing as adding the y and z first, and then adding on the x. 1 plus 2 plus 3 is the same thing as 2 plus 3, and then plus 1 on later. Or in other words, we say addition is, this one's commutative. Sorry, I should have said that at the beginning. This says addition is commutative. You can add in any order you want. This one says addition is associative. I can associate those two together first, do the sum, and then add on that. Or I can associate those two together first, and then add on that. This one, undefined symbol, 0. There exists something out there called 0. Such that for all x, x plus 0 equals x. 0, let me write our undefined terms. 0, 1, plus, times. These are undefined when we are doing arithmetic, when you're doing algebra. So there exists some special thing out there called 0, such that for all x, x plus 0 just gives you back x. We call 0 the additive identity. Why is it called the additive identity? Because when you add with it, you just get back identity, yourself. Take x, take anything you want, add on 0, you get back that thing. This one says, for all x, there exists a y such that x plus y equals 0. For any x, you can always find a y such that their sum is 0. If I pick my x to be 100, then the y is negative 100. Now we repeat those, except for multiplication. So here it was for addition. Now we're going to repeat those same exact things, basically, for multiplication with one caveat. So this one says, for all x and y, x times y equals to y times x. Or in other words, multiplication is also commutative. This one says, for all x, y, and z, if I multiply the x and y first, and then multiply on the z, that's the same thing as multiplying the y and the z, and then multiplying on the x. Or in other words, multiplication is associative. This one now, just like we had our additive identity, this is our multiplicative identity. There exists some magic thing out there in existence. We're going to make up a symbol for it and call it 1. There exists something called 1, such that for all x, 1 times x just gives you back x. So multiplying by 1 just gives you back whatever you had, the same way adding by 0 just gives you back whatever you had. So 0 is called the additive identity. 1 is called the multiplicative identity. And then, similar to this one said for all x there exists a y such that x plus y gives you the additive identity. This one says for all x, where x isn't 0, there exists a y such that x times y gives you 1. Or in other words, the multiplicative identity. If I give you any number x, you can find a y such that their product is 1. If I give you 2, 2 times what equals 1? What can I multiply 2 by to get 1? 1/2. What if I gave you 7 here? What can you multiply 7 by to get 1? 1/7. What if I gave you pi here? What can you multiply pi by to get 1? 1 over pi, whatever that is. 1 pi. Pi times 1 over pi gives you 1. What if I gave you 0 here? It said in the case where x isn't 0. So you're breaking the rules here. What if I give you 5/3? 3/5. You just flip the reciprocal of whatever I give you. If I give you x, you just give me 1 over x, whatever its reciprocal is. And it will always and forever be 1. Make sense? Our next one is our rule for distribution. You already know this one. So sorry, the first 4 were addition, the next 4 are multiplication. The next one tells us how addition and multiplication work together. What happens when you're both timesing and multiplying in the same line? So if I have x times y plus z, then the x distributes over the addition. So x times y plus z is the same thing as x times y plus x times z. So that tells you how to go back and forth between addition and multiplication when they're both together. And then finally, our last axiom is what we call our non-trivial axiom, which is that 1 and 0, whatever they are actually different numbers. And that's it. Those are all the assumptions we make on the real numbers. The author is not going to go through any of these. He's going to assume that you already know these in some sense. And he's also not going to now define everything like we're going to define it. Notice what we have defined over here. Notice all the symbols we have so far that are non-logical symbols are 0, 1, plus, and times. All the other symbols that show up here are symbols of logic. The for all there, that's a quantifier. That's a logical symbol. The equals, that's a logical symbol. The parentheses, those are symbols of logic. The only symbols that show up here that are not symbols of logic are the 0, 1, the plus, and the times. And we now use those to define everything else we talk about in arithmetic. Give me something you talk about in arithmetic. Something really simple. You talk about 2. So here's a symbol you have in arithmetic. 2. If I'm going to define 2 now, I have to define it using just these symbols. And so we are going to define 2. Colon means we're defining a new symbol. On the right-hand side, we're going to write the symbols that we've seen before. And we're going to define that to be 1 plus 1. There's our definition for 2. Now, how on earth do I know that 2 is something different from 1 plus 1? Maybe 1 plus 1 actually comes out to just 1. How do I know that 2 isn't secretly just 1?
Because 1 plus 1 giving you 1 would mean that 1 equals 0.
Because it's going to get contradiction here. We know 1's not equal to 0. Let's go over that. Proof. I'm going to do a proof now that 2 is not equal to 1. I'm going to do a proof by contradiction. I'm going to show that if 2 equals 1, it leads to something impossible. Remember, one of the ways we can prove it, if I know alpha implies something false, something impossible, then alpha has to be false. So I'm going to, 1, assume my alpha, and typically if I'm going to show it implies false, just for my reader, I say assume by way of contradiction. We say that a lot, and so we put B, W, O, C. Assume by way of contradiction that 2 is equal to 1. I'm going to show that this leads to something impossible, therefore 2 is not equal to 1. Then, let's see. Sorry, 2. 2. There exists something out there, I'm going to call it Y. Y such that 1 plus Y equals 0. How do I know that? How do I know that there's something I can add to 1 to get 0? Which axiom tells me that?
4.
Axiom 4. Axiom 4 here says for any x, there exists some y such that their sum is 0. So my x here is 1. I know that for 1, there must be some y such that their sum is 0. So what is y? In our heads, we know it's -1. But so far, I don't know what y is. It's just whatever you add to 1, you get 0, which this axiom tells me exists. So 3. Then 2 plus y is equal to 1 plus y. How do I know that? I know 2 equals 1. How do I know 2 plus y is equal to 1 plus y? How do I know I can add the same thing to both sides? It was using both. It was from that theorem of logic that we proved. It was from this theorem of logic. If A equals to B and circles any operation, then A circle C is equal to B circle C. So we use both these principles to do this proof, but now that's a theorem of logic. That you can add the same thing to both sides. So I know I can add the same thing to both sides. There we go, we did it. What is 1 plus y equal to? 0. So, 3. Then, really quick, let's rewrite out what 2 is. 2 by definition is?
You're on line 4, by the way.
1 plus 1. By definition.
Line 4, by the way.
Sorry, what?
You're on line 4.
Thank you. That's what you were saying. Okay. Then 1 plus y, just rewriting this side, plugging in the definition 2, is equal to, we'll leave that as 1 plus y for a second. Okay. Next, I'm going to use the rule of associativity, which says if I had the parentheses here, I can shift them over 1 and put them there. So I'm going to take these parentheses and shift them over. So then, 1 plus y is equal to 1 plus y. Now finally, well not finally yet, what does 1 plus y equal?
0.
0. So, 6, then 1 plus y, which is 0, is equal to 1 plus y is 0. Now what's 1 plus 0? Hold on. 1 plus y is equal to 0. Doing that substitution here. What's 1 plus y? 0. How do I know that? Y is the thing I know exists, such that 1 plus y equals 0. This axiom told me that for any x, there must exist some y, such that x plus y equals 0. My particular x was 1. So I knew 1 plus y equals 0 from axiom 4. Okay, so going from here to here, just replacing my 1 plus y's with zeros. And now, what is 1 plus 0? How do you know that?
Because 1 plus anything is equal, or 1.
Axiom 3.
Yes.
Axiom 3 that there says there exists some special number out there called 0, such that for any x, x plus 0 is just that x. So axiom 3 is what tells me how to add with 0. Just like axiom 7 tells me how to multiply with 1. So 1 plus 0 from axiom 3 we know is just 1. So 7. Then then we get 1 is equal to 0. Now how do I know 1 cannot be equal to 0? Yeah, 8. Then 1 equals 0, and 1 is not equal to 0, which is a contradiction. Usually we write back and forth arrows like that to say something false. So we got 2 equals 1 implies 1 equals 0 and 1's not equal to 0. But that's impossible. I can never have a statement and its negation both being true. So 2 equals 1 imply the contradiction. So 9, therefore, 2 is not equal to 1. And our proof is done. Because if 2 were equal to 1, then we get a contradiction. That's a big proof for showing that 2 is in fact different from 1. Okay, so I know 2 is not equal to 1. How do I know it's not secretly 0? Well, we won't do that proof. And so now we have 2 defined. And it is in fact a different number. And now how can I define the number 3?
2 plus 1.
Yeah, 2 plus 1 now is what I'll call 3. Remember at the very beginning of the class last week, I asked you for a definition of 4, and Caleb just said 3 plus 1. And it kind of felt like he was almost cheating somehow, like just making up something. Here's where that came from. 3 now is defined to be 2 plus 1. And we can prove that 3 is in fact a different number from 2, but we won't go through that. And then 4 now is defined to be 3 plus 1. And 5 is 4 plus 1. And 6 is 5 plus 1. And now we can define all these whole numbers. How do we define the negative numbers? That now comes from this axiom. I know for any number x, namely 4, there has to exist some y that makes the sum 0. We call that y negative 4. So what is negative 4? By definition, we call all the y's here the additive inverse of the x. We make negative 4 the additive inverse of 4. It's a number that when you add to 4, you get 0. That's how you get negative 4. So you can define your integers, and then you can use this one now to define, or sorry, not that one. This one now to define all your fractions. What is 1/2? Since now we know what 2 is, 1/2 is a number that you multiply 2 by to get 1. Or in other words, it's 2's multiplicative inverse. And that's how we define it. So now we can define all these numbers, all the integers, and all the fractions. All from these axioms. Just trying to give you a taste for how we would do that. Now this is very heavy duty. Your book's not going to do this step. I'm giving you all the foundations. The book's going to skip over all that. And they're going to start with, we're not going to try and define what plus means or what the number 5 means or anything like that. But just to sink it in now, let's go back and prove 2 plus 2 is 4. And it will be nice and simple. So prove 2 plus 2 is 4. All right. What does 2 plus 2 equal? What's our definition of 2?
1 plus 1.
1 plus
1
1.
plus 1. So 2 plus 2 is the same thing as 2 plus 1 plus 1. You with me? Now, associativity here says if I got the parentheses here, that's the same as having them here. Tells me I can move my parentheses like that. You with me? So this is just equal to 2 plus 1 plus 1. Now 2 plus 1 by definition is going to be 3. So this is equal to 3 plus 1. And 3 plus 1 by definition is 4. So we just barely proved it. 2 plus 2 is in fact 4. And there you go, the whole proof. It's not a hard proof, it's a very easy proof. The odds are you were never taught to prove that way before. Okay, and so now we are ready to actually jump into our textbook. We've laid all the foundations. The textbook will start much easier than where I started. Don't worry. If you've been reading your textbook, like hopefully you should, then you'll notice it starts out a lot nicer. Oh, I didn't change the theme on these. Does that white show up okay? Let's see. How do I change the theme on the fly? Let's take a break while I figure this out so you don't have to watch me do it. It'll take a couple minutes. And then we'll start on the book when you get back. So now, for the second part of this lecture, and the easy part of the lecture, this is going to be the only part that you have any homework on. Everything leading up to now was just trying to give you all the foundations you would need for everything. So section 3 in your book, it's called definition, and here we're just going to introduce a bunch of definitions now that are going to be used pretty much throughout the rest of the book, so you got to get used to them. So let's start with a very simple definition. First, we're going to start out with even. What does it mean to call something even? What's an even? What's an even? Come on, what's an even? Give me one.
2.
4, 2. What are those evens? What exactly is the definition of even? Let's make sure you know what even is. You've been using the word for how long now?
6 years at least.
What does it mean to call a number even? So an integer, notice that it has to be an integer. An integer is called even, provided it is divisible by 2. So there's our definition of even. Now, if you're looking at that, that kind of raises some other questions. What does it mean for something to be even? I said it's an integer is called even, provided it is divisible by 2. What on earth do these other words mean? If I'm going to understand the definition, I have to understand all its components. So I need to make sure I understand what exactly an integer is. I need to know exactly what divisible means, and I need to know what 2 means. Now, what are the integers? What are the integers? Tell me. Negative infinity through infinity, so what about negative 1/2? Is that an integer? No, what are the integers? They're all the whole numbers, both positive and negative, right? Integers. So, we use a z with an extra line to represent the integers. That will never go away, you'll see that 100 times. This means a set of all integers. What does this mean? It means all the numbers, negative 3, negative 2, negative 1, 0, 1, 2, 3. You know what the dot dot means? It means continuing that pattern. Keep counting up and keep counting down. That's what all the integers are. Now, the author in the book, he says, what's the definition of 2? He says, well, we're not going to define everything. We're going to take 2 as a starting point. But now I gave you guys the foundations for defining 2. So what's the definition of 2? 1 plus 1. What's the definition of 3?
2 plus 1.
And so using those axioms, we could have actually defined each of these integers. So you know how to define all these, at least theoretically, from those axioms. And now we take the set of them as all the integers. So you know what 2 is now. You know what the integers are now. What remains to be defined is divisible. What exactly do we mean by divisible? So now we're going to define divisible. Let a and b be integers. Integers is now defined. So now, so far we're good. We don't need to define anything else. Let a and b be integers. We say a is divisible by b, provided there is an integer c, such that b times c, sorry, I didn't put the times symbol there. You know when 2 letters are right next to each other, the times is implied, but should have put it there. B times c equals a. Now times, what's the definition of times? Bad question. If we look at our axioms on the numbers, that tells us what times mean. Equals, where did we define equals? We don't need to, it's a symbol of logic. Equals was given its meaning through the law of identity and the principle of extensionality. So now, everything here is perfectly good. We've defined everything up to this point, or we're talking about axioms we know about. We also say b divides a, provided b, we also say b divides a, or b is a factor of a, or b is a divisor of a. The notation we use is b divides a. That's how we read that. So what does it mean to say b divides a? It means that there exists some other integer c, such that b times a, such that b times c equals a. This is not divided by, this is divides. So, let's do some examples. Does 2 divide 8?
Yes.
How do I know 2 divides 8? What is the magic c? 4. Since I can find some integer, namely 4, such that 2 times 4 equals 8, then 2 divides 8. Let's try another one. Does 3 divide 8? No. How do I know? There is no magic integer I can find such that 3 times that integer equals 8. You cannot find an integer c that makes this true. So what does it mean to say that b divides a? It means that there exists some integer c such that b times c equals a. That's what it means to divide. We will use a vertical line for divide, straight up and down. 2 divides 8 is true. It's a statement. Divides is a predicate, takes 2 terms, spits out true or false. 2 divides 8 is true. 2 divided by 8 is 1/4. These are not the same thing. The language just happens to be similar. Divides, not divided by. Good? So, true or false to each of these? 4 divides 8. True. How do we know what's our magic number? 2. That's how we know. Because 4 times 2 equals 8. Does 8 divide 12? Since 4 goes into both of them, what does that have to do with anything? 8 divides 12? False. So maybe put what they are. This one was true, and we know that because of 2. This one is false. 8 does not divide 12. There's no number I can multiply 8 by to get 12. Does 3 divide 5? No, because there is no integer I can multiply 3 by to get 5. Does 27 divide 3? 9. This one's true, right? No. It's not saying 3 divides 27, it's saying 27 divides 3. There's no integer I can multiply 27 by to get 3, so this is false. 0 divides 1. Does 0 divide 1? Is there any integer I can multiply 0 by to get 1? No, so 0 divides 1 is false. 1 divides 0? Yes, in that case it's true. What about 528 divides 0? Is there an integer I can multiply 528 by to get 0? Yes. What is it? 0. And so x divides 0 is true for any integer x. Because you can always just multiply by 0. Okay. Does negative 3 divide 3?
Yes.
If it divides it, you better be able to give me the integer. What's the integer?
Negative 1.
-1. So this one's true. Because there was some integer I could find, such that negative 3 times that integer gave me 3. Does 1/2 divide 5/2? Or sorry, does 1/2 divide, does 0.5 divide 2.5?
Yes.
Yeah, because there's an integer 5. 0.5 times 5 equals 2.5. So 0.5 divides 2.5. No! This doesn't even make sense. Our divides applies to integers. This makes as much sense as asking me, what is red divided by the sea? If I take red and I divide it by the sea, what do I get? Neptune, of course. Doesn't make sense. You can't just plug in anything. These things are only defined on certain domains. So don't think that that makes sense. That makes no sense. That's gibberish. Divides is only defined when we have integers. Let a and b be integers. Make sense? Okay, does 99 divide 0? Yes. So in this case, it's true. Okay, any questions on any of those? So now, we know what it means to call something even. We covered all its component pieces. So now, an integer is even. An integer is called even, provided it is divisible by 2. We now know what integer is, we know what divisible is, and we know what 2 is. And so now we know what it means to call something even. Hey, look at that. Learning even. Move on to our next one. Bet you can't guess what word we're going to define next. It's an odd one. Okay, so now what is the definition of odd? Give me an example of an odd number.
31.
What? 31 works. 31's odd. What else is odd? What? 7. What else? 1. So an odd number is just a number that's not even, right? What about pi? Is that even or odd?
Question's not.
Bad question. It's So not every number is even or odd. So we can't say a number is odd provided it's not even. So what does it mean to be odd? An integer, so odd only applies to integers. An integer a is called odd, provided that there exists an integer x such that a is equal to 2x plus 1. If I can write my number a as 2 times an integer plus 1, then it is odd. Is 19 odd? Then I better be able to write it as 2 times something plus 1. What is the x that goes there? That's not a 20. That just means fill in the blank. Sorry. 2 times what plus 1 equals 19? 9. And so yes, 19 is odd. How do I know? Because it's equal to 2 times an integer plus 1. Okay, let's try, really quick, let's try 2. Is 2 odd? If 2 is odd, then it has to be 2 times some integer plus 1. What can I plug in here to get 2? Well, let's say if I plug in 0, I get 1. And if I plug in 1, I get 3. How can I get 2 out of that? I can't. Because 2 isn't odd. If I can write it as 2 times an integer plus 1, then it's odd. I can't write 2 that way. So 2 is not going to be odd. Okay, what about 57? Is 57 odd? How do you know? What's our magic number there? 28. 2 times 28 gives me plus 1 is 57. There we go. Proof that 57 is in fact odd. What about 1? Is 1 odd?
Yes.
How on earth are we going to do that? Times 0. 2 times 0 plus 1 is 1. So 1 is in fact odd because it's 2 times an integer plus 1. Okay, what about 11? Is 11 odd?
Yes.
How do you know?
5.
5. 5 is the magic number. Perfect. What about negative 11? Negative 5. Let's see. 2 times negative 5 is? Negative 10 plus 1 is? Negative 9. Negative 10 plus 1 is negative 9. That does not equal negative 11. Oh, that's what you were saying. Plug in negative 6. So plug in negative 6 is our special number. Negative 6. What's 2 times negative 6? Plus 1 is? Negative 11. Woohoo! It worked. That is in fact odd. All right, let's try another one. Negative 57. Is that odd?
Yes.
How do you know?
Negative 29.
Negative 29. What's negative 29 times 2? Negative 58 plus 1?
Negative 57.
It worked. There we go. So now you know what it means to be even. Now you know what it means for one number to be divisible by another number or to divide another number. And now you know odd. So those are the 3 definitions we covered so far. Never going away. You're going to use these definitions 100 times. Even, divisible, odd. Those 3, never going away. What's another one that's never going away? One that you've used 1,000 times. A prime number. You've heard about these before. They're your favorite kind of numbers. Let's read its definition very carefully. An integer p. So what do I know about a prime so far?
It's an integer.
It's an integer. An integer p is called prime, provided that it's greater than 1. And the only positive divisors, we now defined what it means to be a divisor, what it means to divide. And its only positive divisors are and the only positive divisors of p are 1 and p itself. So what does it mean for the number to be prime? It has to only be divisible by 1 and itself.
So is 1 not a prime number?
So 1 is not a prime number. How do I know 1 is not a prime number?
Because it's not prime.
Because by definition, our primes have to be greater than 1. By choice of our definition. We get to choose how we define these things. And we choose what we mean by numbers that are greater than 1, and their only positive divisors are 1 and the number itself. We decided we're going to call that a prime. Okay. So, if a number is not prime, then it must be composite, right?
No.
No, not necessarily. So we have primes and we have composites. These are the 2 we often pair together. What does it mean for a number to be composite? A positive integer, a. So what do we know about a so far? It's a positive integer. And it's called composite, provided that there is an integer b, where b comes between 1 and a, and b divides a. If I can find a number between 1 and the number a that divides it, then a is composite. Okay, so let's play a game. We're going to play a game called prime or composite. The number 3, is this prime or composite? Prime is the only integers, the only positive integers that divide 3 are 1 and 3 itself. What about 11? Prime. 15.
Composite.
How do you know? You better give me a number. 3. So 1 is less than 3 is less than 15. And 3 divides 15. That's what it means to be composite. A number a, in this case 15, is composite, provided there exists some integer b between 1 and 15, such that b divides a. So since 3 is between 1 and 15, and 3 divides 15, 15 is in fact composite. Now, we could have also used the integer 5. So these integers will come in pairs. In this case, 3 and 5. Typically come in pairs. Sometimes it could be the same integer twice. Like with 25, it's 5 and 5. Okay, prime or composite? Composite. How do you know? 4. Because 4 is between 1 and 8, and 4 divides 8. Prime or composite? Composite. 4. Obviously, all our evens are divisible by 2. Okay, 2.
Prime.
It's an even. It's divisible by 2.
Wow.
So it's composite. No, that line of reasoning does not make sense. Is 2 prime or composite? 2 is prime. What are numbers is 2 divisible by? 1 and 2. 1 is the number itself. Is there an integer between 1 and 2? Can I find some integer between 1 and 2 that divides 2? No, because there isn't an integer between 1 and 2. So it's not composite, it's for sure prime. Now, what about 1? Prime or composite? Neither. It's 1. So 1 is not prime and 1 is not composite. 97. Prime or composite? In this case, happens to be prime. Just seeing how well you know your prime numbers. What about -7? Prime or composite? Neither. Why can't it be prime?
It has to be greater than 1.
Oh, it has to be greater than 1. And -7 is not greater than 1. But why can't it be composite?
Because it's a positive integer.
Well, because it's not a positive integer, and composites have to be positive integers. 16? Composite, how do we know? 8, 4. -16? Why isn't it composite? It has to be a positive integer. It's not a positive integer. What about 0? It's not greater than 1, so it can't be prime. And it's not a positive integer, so it can't be composite. What about 117? Prime? That one's composite. You can go play with it. Always leave them scratching their head with at least one, right?
Yeah.
Okay, so let that bug you as we keep moving forward. Actually, we've already covered the next section, which was just about the outlines of proofs. So there you go. So what are the big bad definitions we introduced today? These are words you've never heard before. They are even, divisible, odd, prime, and composite.
What kind of monster decided 9 times 13 would be?
Who decided it? Those me mathematicians.
I don't know.
Getting together and deciding how math comes out. Okay, so those were our 5 definitions, right? Did I miss one? You already knew integers, blah, blah, blah. So even, divisible, odd, prime, composite. Those are never going away. You need to know those 5 definitions. And you need to not just have a feel-good intuition for what they mean. you need to know exactly what their definition means. So just to stress it, let's close that and let's talk about each of them again. What does it mean to be even? How do I know if x is even?
If it's divisible by 2.
It's divisible by 2. If 2 divides x, then x is even. Or I think we were using like a's and b's, so I'll try and stick with that command. Alright, that's what I meant to be even. 2 divides it. 2 divides it, or in other words, 2 times an integer equals a. So the other way we could have written that is a can be expressed as 2 times some integer. Same thing. If 2 times an integer gives me a, then 2 divides a. Or in other words, a is even. Here's typically the way we're going to want to write it. If I know a is even, I know 2 times something equals a. 2 times some integer equals a. Okay, what does it mean to be odd?
2 times some integer plus 1.
A is equal to 2 times some integer plus 1. If it's expressed this way, it's even. If it's expressed this way, it's odd. Okay? Divisible. What does it mean to say that A divides B?
That there is
There exists some other integer x such that ax equals b.
yeah.
That's what it meant to say A divides B. When we said that 2 divides 8, it's because 2 times some integer equals 8, namely 4. So there's the equation you would use to express that relationship. Okay, so that was even, odd, divides. What was our other one? Prime. What did it mean to call P prime?
Greater than 1.
P is greater than 1. Yeah, and 1 divides P, and P divides P, and those were its only positive divisors.
You missed another thing on your prime.
Thank you. And then finally, composite. What did that mean?
P is a positive.
We'll use C for composite. How do I know C is composite?
Positive integer.
So C is greater than 0. It's a positive integer. And what else?
There's something between.
Yeah, we can find something. 1 less than A, 1 less than C, such that A divides C. And that. That was like equivalent. Okay, so those are going to be our 5 big bad definitions. Never going away. You gotta get comfortable with these things. We're going to be doing proofs with these definitions over and over again. That's it for that. And that is it for the material. We already covered section 4 with proof stuff. Your hardest homework will be section 3, and it won't be too bad. Section 4's homework will pretty much just be what you already did in your handout. It will be rephrase these statements as if-then statements type stuff. Any questions you want recorded before we jump into homework? Okay, we'll call it there and start with our homework.